Welcome back to Physics with Mr. McQueary. Today we're going to be talking about calculating the forces on an object, aka net forces, determining those forces, and also talking about if we do have the net force, how do we find that missing force component in there? So 2 learning targets today: determining the net force of an object, and then determining the magnitude of the forces if we are given the net force. So essentially, we're working backwards from the first learning target. Once again, I'm going to introduce our common forces that are at play whenever we make a free body diagram. We have weight, normal force, friction, a push-pull, and tension. We want to make sure that we're going to have these in mind as we work towards these that we're solving today. When it comes to calculating the net force, one of the things we can take advantage of is that just like projectile motion, your horizontal components and your vertical components are independent of each other. One of them does not affect what the other one does. So you can see there we have kind of a visual where we have up or to the right, we consider that positive, and to the left or down, we consider that negative. Okay, so what you're going to find when we work through these is that we keep X separate and we treat Y separate. So if you don't like horizontal and vertical, think X and Y. We're going to treat those separate, and neither one of them has an effect on the other one. First, let's break this down into one dimension. Sometimes if we do 2 dimensions at first, it can get really complicated really quickly. So let's kind of build up to that. If you're given a cart like this and you have 2 forces pushing on them, you can probably calculate the net force just like that. 60 plus 30. You have a net force of 90 newtons to the right. You just add them up because the vectors are working together. Now consider a situation like this where your vectors or your forces are working against each other. So instead of adding them together, you're going to be subtracting. 30 minus 10 gives us 20, and most of that is to the right. Actually, all that's to the right, right? Nothing's left over once we subtract on the left side. So there's an example of forces that are working together, forces that are working against each other in one dimension. When we take this and we expand it to 2 dimensions, we're going to do the same thing we just did, but we're going to work on these components separately. So let's look at the horizontal component. Horizontal means X. 20 newtons is to the right. That's positive. To the left, it's 3 newtons. And we have a negative in front of there. Remember, if you go left or down, that's negative. So the difference, or when we add them together, is 17. So 17 is left over. That is the net force in the X direction. Look at the Y direction now, or the vertical component. We have 6 going up, 6 going down, making that a negative 6. So when you add those together, you get 0. So we have 17 newtons that are left over, and because it's positive, it must be going to the right. That's our net force. Let's do another example of net forces. This time, we're given a mass in the middle, and it turns out it doesn't matter one way or the other. They could give us any mass they wanted. That net force would be the same. So the horizontal component, this way, we have 15 to the right, 45 working against it to the negative. So that means that the difference will be negative 30, or 30 newtons to the left. And the vertical component, 45 up and 45 down, means that that is a balanced force in the vertical component. So what do we have left over? 30 newtons to the left. Let's look at this component over here, the horizontal component first. To the right, we have 80 newtons. To the left, we have 10. And we put that negative on there because it's to the left. The difference is 70. Now, in the vertical component, we have 90 going up, 90 going down. That is a balanced force. Therefore, there is no difference. And the only net force is that 70 we found in the horizontal component to the right. That's just the first learning target, determining the net force. The second part is to give you the net force and then work backwards to find the individual forces that are acting on the object. Let's bring our carts back again. We know that the overall net force will be 60 newtons to the right. There's already 40 in that direction. What plus 40 will get you to 60? Obviously, 20 newtons to the right will get you there. So the missing component is 20 newtons. Now let's do one where they're working against each other. The net force we know is 9 newtons to the left. We have 15 newtons already going to the left. So 15 minus what will give you 9? Obviously, it is 6 newtons to the right. 15 minus 6 will give you 9. So that is the simplest version. Now let's put that in multiple dimensions. In the horizontal component, we have a missing applied force that we don't know. To the left, we have negative 20 newtons, and the difference is 95. Now let's do this in 2 dimensions. The horizontal component to the right, we don't know. That applied force is missing. We have to solve for it now. To the left, we have 20 newtons. The net force has already been given to us of 95 newtons to the right. So we can go ahead and ignore the vertical component because those cancel out. You have a balanced force. Or you could say equilibrium. So in the horizontal component, we have to figure out, okay, what is that missing right force? Well, remember when we did the guess method? That comes back again. Our given is that the net force in the x direction, or the horizontal component, is 95 newtons. The unknown is the applied force to the right. So our equation would go as follows. That net force is equal to the applied force minus the friction force. When we substitute in our known variables, we find out that an applied force must have been 150 newtons to the right. It's the same thing we did with our carts, it's just it took an extra step to set this up. Another example here with a missing force, this time it is to the left. We have a horizontal component, once again, that we're dealing with because the vertical components have a net force of 0. We have 18, and then we have something that we don't know that's working against it. That will equal 6 newtons to the right. So let's go ahead and set it up over here. Basically, we plug everything in over here, and we see that 12 is that missing number. And you could probably do this in your head. Because you had 18, you had to get to 6. 18 minus what gives you 6? 12. So if you're somebody who struggles maybe a little algebraically and needs to write out all the equations, that's probably not a bad idea. If you can solve it in your head, good luck. Now let's talk about the normal force that's missing. So we've given you a couple problems over here where it's been the horizontal component we've been dealing with. Well, this time we're worried about the vertical component. What's unique about this problem is that the net force is 0, both in the horizontal and the vertical component. So if you have a force of 50 newtons pointing down, and you need something to balance it out so that it gets to 0 for your net force, what plus negative 50 will give you 0? Well, you could solve for it, or just realize that negative 50 plus 50 gives you 0. It's like going to the beach. You dig a hole that's 50 meters, well, 50 meters would be a really deep hole. Let's say 50 inches deep, which is still pretty impressive. But then you fill it in with 50 inches of sand, it levels out to 0. That right there will give us both learning targets for the day. The first step was determine the net force that acts on an object. The second part was to go ahead and go backwards from the net force to find the individual missing forces by using components, using the x and the y component independently. Until next time, see ya.